So what you can do is we can start with number 1, which I did complete. And let's talk about, again, we're graphing our bounds. And then anytime you have f of xy, the xy is called our objective function. That function is the function you are trying to minimize or maximize. So when we look at these types of problems, I know I'm not graphing the f of xy equation. So you don't graph the objective function. You only graph the functions in which are considered constraints. Okay? Yes.
Okay, so is it always going to be like an exact point on the graph for the plug into the equation?
Yes. It's always going to be a point that's like a corner of intersection between two of the lines. So like here, here, there, and there. So if you look down at number 9, this is a equation in which there's only an x value. So that tells me that it is two vertical lines. So the x values are going to live between -3 and +2. So again, the x values are going to live between -3. Hold on. Sorry. We had somebody join the Zoom, so I had to unmute, but then it echoed. There you go. All right, so between -3 and 2, so you graph at -3. It is a solid line. You graph through 2. Also a solid line. And then what we're going to do from here is shade between them. So that represents our first equation. So that is a domain constraint. You are limiting your x values from -3 to 2. And then we have another constraint. We have a constraint on y, where it goes through -6. It has a slope of -2. So we're going to just play it backwards. So already I can see that I have a point of intersection here. And if I continue down 2 and over 1 and down 2 and over 1, there would be another point of intersection potentially down here. This line is solid. And the y values are greater than, so we're going to shade above. So I now have a trapezoid of intersections. And then we have one last constraint. So that is this line here. What I'm going to do is just divide everything by 4 so that my line is y less than or equal to 2/4, which is 1/2 x plus 8. I'm going to go through my y-intercept of 8. And then my slope is up 1 over 2, or down 1, so that's at 7, -2. And then you go through your point here, and over there. And in all fairness, probably should have gone by 2s just so my graph was more clearly graphed for you. And these are y values less than, So you're going to shade below. So again, we know that the points of intersection, you can see two of them. They occurred on this line right here. So one of them happened at -3 and 6. The other one happened over here at -3 and 0. So we're going to plug those points in to my equation, because those are the points of concern. Now we know that there's a point happening down here, and again, we know this x value is 2. So you could actually just plug 2 in to that purple equation. So -2 times 2 is -4, -4, -6 is -10. So this point is going to be 2, -10. If you can't see it perfectly on your graph, even though we know it exists down there. And then same with this this green line and the red line. We know that this is x equals 2. So you could plug 2 in here. 2 times 1/2 is 1. 1 plus 8 is 9. And our other point, like I said, occurs at -3. So that is plugging -3 into that purple graph. So you'd have -3 times 1/2, which is -1.5, plus 8. So you take 8 minus 1.5, and you get 6.5. Does that help for seeing and understanding where some of these points are coming from? And then from there, you just plug those points in for x and y. When you're plugging them in, the x value is changing and the y value is changing. But what's not changing is the 4 or the 9 that you are multiplying by. So even on my calculator, what I like to do is sometimes just type this in the first time and then get my answer. And then if you have one of the newer calculators, you can actually arrow back up and hit enter, and it will copy and paste everything you've typed. So you can just arrow through and change the numbers you plug in. So I can arrow up, copy and paste. And again, a lot of times the numbers repeat. Oops. So we could see that the function is maxed at 82 and it is min at -89. Good? Yes.
So you just plug in vertices for
Yep. So whenever you're solving these, the points you're plugging into the objective function are your vertices. That's the vertex principle, because the idea is that those vertex points are always going to be the maximums or the minimums of each graph. Do you want to do one more from this homework? And then we'll look at the, I'm guessing you're going to want to see the word problems. Yeah, it's always the word problems. So in this graph here, we have -2 for x and then up to +4. So I'm just going to be safe. I'm going to go by 2's this time. So I'm going to treat this like -2. And this as +4. Then we're going to shade between. And then on Y, it's from 5 to 8. So again, I'm just going to go by 2s. And then our last equation, you could, again, plot your intercepts. You can solve this for Y. And one of the things I talked about the other day was that obviously 26/3 is not going to be a nice starting point. However, if I plug in 0 for Y, that would put me on this line right here. I could find my x-intercept, and my x-intercept would be a nice starting point. So your x-intercept would occur, Y is equal to 0. And in this case, if Y is 0, then the x-intercept is 13. So it might be easier to plot or start at that type of point. So you have 2, 4, 6, 8, 10, 12. So of course it's right off my graph. So we have that point at 13, 0, which is at least not a decimal. And now we apply our slope of -2/3, which is the same as saying up to and over 3. And you can see in doing that, I actually have the intersection of these 2 points right here at 1 and 8. And you can always check yourself by plugging 1 back in and seeing if you get 8 out as your answer. And again, in this case, we know we would, because 26 minus 2 is 24. 24 divided by 3 is, in fact, 8. So I know for certain one of my vertice points is 1, 8. Does that make sense how I kind of already knew that just from the graph? Now you need to determine, okay, does this one shade above or below? So the purple graph is shaded below. So that's going to give me this region in here. But the overlap, or the solution region, is where all those graphs occur. So it's kind of like this in here. So my vertices are that 1, 8. This point of intersection here, which is at -2, 8. We have a point of intersection here at -2, 5. And then we have 2 other points of intersection over here, because it gets bounded by the green and by the purple. So this graph ends up with 5 vertices. So you have the intersection between 4 and 5. And the purple graph intersects at 4. And again, if you can't tell from your graph where it's at, so mine appears to be at 6. You could always check by plugging 4 in here. So negative 2 times 4 is negative 8. Negative 8 plus 26 divided by 3 gives you 18 over 3, which is 6. Do you see how I got each of those points if I can't see them clearly on my graph? And then we have to plug all of those in. So you do 8 times 1 minus 10 times 8. And then I would get 8 times negative 2. And if you need to add a number when you copy and paste, you can hit second and the delete key. And that will let you insert a value. And then you can just arrow back and forth. And then we'll copy and paste one more time and write down our answers. So I go negative 72, negative 96, and negative 66. And then finishing out at the bottom, we have 8 times 4, and 8 times 4, but 10 times 6. So I get negative 18 and negative 28. So my largest negative number occurs here. That is our mid. And my largest positive number occurs here. So that is my max. So what I'll do is post the answers to the rest of these worksheets so you can kind of go back through and check them. So I'll put up the answers to 11, 12, 13, 14, 15, 16 as a PDF for you. But I want to take some time and go over the word problems with you. So we have that Jenny's Bakery makes 2 types of birthday cakes. Yellow cakes, which sell for $25, and strawberry cake, which sells for $35. Both cakes are the same size, but decorating and assembly time required for the yellow cake is 2 hours, while the time is 3 hours for the strawberry cake. There are 350 hours of labor available for production. How many of each type of cake should be made to maximize or minimize production? So this problem kind of starts a little bit differently than the other problems. The problem actually begins by giving you the objective function because it's giving you the cost and you're trying to maximize revenue. So the cost is going to maximize her revenue. So we'll say that X is yellow cakes and Y is strawberry cakes. So X is yellow, Y is strawberry. And then that gives that this cost or revenue function is 25X plus 35Y. It says they're the same size, but their assembly and that time differs. So the assembly time for a yellow cake is 2 hours, and the assembly time for a strawberry cake is 3 hours. So what we're graphing is essentially our total number of hours. And our total number of hours is 350. So what that means is X plus Y has to be less than or equal to 350. And then we have to take into account the hours to produce each cake. So it's 2x. I didn't leave myself space in the right spot. And 3y. And then each cake could be produced where you only produce that cake. So you could also have 2x alone less than or equal to 350, or 3y alone less than or equal to 350. And those would represent your x and y intercepts for that graph. So what that means is you could make a total of 175 yellow and no strawberry. Or you could make a total of 116 and no yellow. So we have to plot those points. So I kind of copied and pasted all these. I would honestly ignore the x and y intercepts and redraw them so that my graph was in the corner. And for your homework tonight, I did adjust this. This one came from your book, such that I have my yellow over here, strawberry over there, and then we're going to maximize. So we know that we need to go out to 175 and up to 116. So I'd go by 25s. So this gives a constrained region that is a triangle, and the reason for that is because our vertices also fall in the corner functions. So if we want to maximize our revenue, we're going to plug in each of those vertices to that function. So this vertice here would be making 116 and no yellow. And then the vertice down below would be making 175 yellow and no strawberry. So max revenue would occur if they made all yellow cakes, which should make sense because the yellow cakes take less time to produce. Better? Okay. The manager of a travel agency is printing brochures and flyers. So one of my variables is going to be brochures. The other is going to be flyers. They're advertising discounts on vacation spots during the summer months. Each brochure costs 8 cents to print, and each flyer costs 4 cents to print. A brochure requires 3 pages, and a flyer requires 2 pages. The manager does not want to use more than 600 pages, and she needs at least 50 brochures and 150 flyers. How many of each should print to minimize cost? So easiest thing is to know and understand your variables, we'll say X is brochures and Y is flyers. And we know we need at least 50 brochures. So X has to obviously be greater than or equal to 0, but then in the case of this problem, it has to be greater than or equal to 50. So we always have a constraint or bound of 0 when it comes to producing an item, but in this case, the company has a minimum constraint of their own. Then the second part is that they need 150 flyers. So Y has to be greater than or equal to 150. So again, graphing those two constraints, I'm probably going to move my graph to ignore the X and Y intercepts or axes. I'm going to redraw them in over here. I'm going to go by 25s again. So here's my 50. We know that at 50 we're going to shade to the right. And then draw in my 150. And shade above. So I already know that I have one of my vertice points probably, and that point is going to be the point at which it's the minimum number of each they could produce. So the minimum number they can produce is 50 and 150. And again, that's coming from the idea that that is the minimum amount allowed. And then it says a brochure requires 3 pages and a flyer requires 2 pages. So we're going to put those constraints to my words. So we have 2x, or 3x rather, plus 2y has to be less than or equal to 600. So we'd get our x and y intercepts, or solve for y to get our graph. So you get y is less than or equal to negative 3/2 x plus 600 divided by 2, which is 300. So that means my y-intercept is 300. And then I'm going down and over. So really though, I want to know what happens when x is 50. So that's my point of intersection right here. That's 225. So I have this point of intersection here, that when x is 50, that we have 225. That's going to be one of my vertice points. And then we're going to apply our slope of down 3 over 2. And I know I'm going to have another point of intersection here when my graph is 150. So that's on y. So again, I could just plug that into y here and solve backwards for x. So it'd be like 600 minus 2 times 150 divided by 3, and that's 100. So my final constraint point occurs when x is 100 and y is 150. So we're going to use those to get, and again, we're trying to minimize or maximize cost. So cost is 8 cents per brochure and 4 cents per flyer. So we're going to take 0.08x plus 0.04y. So to produce 50 brochures and 225 flyers is $13. To produce 50 brochures and 150 flyers is $10. And to produce 100 and 150 is $14. So to minimize your costs, we're going to produce the minimum number possible. Okay? So what I want for you to do today, I have a set of, I've changed that. Your quiz is now next week. I'm going to have more time to review with you. This is definitely a concept I think is important because it applies to like real world examples. Anybody that's going to take AP Econ at all in high school, like this is a lot of econ stuff, and then they'll incorporate supply and demand. So this is, these are actual algorithms that companies would use. Now they have computers that would produce their things, but somebody again has to write the programming for the computers. So a lot of this unit, hence the word linear programming, starts to incorporate computer programming and that type of concept. So again, I think it's a good unit for applying math in the real world and ways you can use math in a career.